So now we're going to talk about functions. So remember, there were two conditions for that you needed to have for a relation to be a function. So definition, a relation f from a set A to a set B is a function if two things must be satisfied. So for the first one, for all A and A, there needs to exist a B and B such that AB is an F. And the second condition is if AB and AC are an F, then B equals C. If you want to think about this in terms of inputs and outputs, the first one is saying every input has an output, and then the second one is saying that every input has exactly one output. So then, remember we used diagrams to represent functions. So let's say A is the set 1, 2, 3, B is the set AB, and let's say our function is going to be 1A, 2A, and 3B. We could represent this with a diagram where you have these ovals representing A and B, 1, 2, 3, and A and B, and then we have arrows that we draw. So here 1 that's paired up with A, 2 gets paired up with A in our function, and 3 goes to B. So that's how we represent them with diagrams. We also talked about the image of a set. So we talked about F of C. We talked about the inverse image. So F inverse of B. We talked about injective or one-to-one. So let's go over the definition of that real briefly. So we're going to say definition, function f from A to B is injective, or you could say one-to-one, if whenever f of x equals f of y, then x equals y. So we also had surjective or onto. So I'll write the definition for that down as well. A function f from A to B is surjective if every element of B is the image of some element of A. So I'm not going to go too much into detail about these. You should know their definitions. You should know how to show something is one-to-one or onto, and also how to show it's not. So if you're looking for an example, here's one that you could do. Show that the function from R to R given by f of x equals 4x is one-to-one. It is injective, but is not surjective or not onto. And then, so I'm not going to do that one, but you should be able to do that. We also had bijective function, so a bijective function is a function that is both one-to-one and onto. And so we also talked about composition. We also talked about the inverse function. When is it a function? So you should review those topics. I want to look at one final kind of example here. So I want to ask if F composed G is injective. I want to ask, must G be injective? So to answer this question, let's think of some examples here. So here I'm looking at a composition, A to B to C. And this first one will be my function F, the second one will be my function G, and I want the overall function to be, the composition to be injective. So maybe let's pick some elements here. A, B, C. Let's pick 1, 2, 3. Let's pick a different number of elements here. Let's go for 4, X. If I want it to be injective, okay, so I want the composition to be injective, so I know from previous results that F, well, okay, I'm not going to say that. We don't have that, but let's make this composition be injective. So the easiest injective is to go straight across here. Now, in terms of our composition, it doesn't matter where this 4 goes to, because there's nothing coming in from A to 4. And so the answer is G does not have to be injective. I could send 4 to Z, and then G is definitely not injective, but the composition is. So if I look at, so my answer is no, G does not have to be injective. And so my counter example for this statement would be, let's see, F is, so my set A is the set A, B, C, B is the set 1, 2, 3, 4, and C is the set X, Y, Z. F would be the function A goes to 1, B goes to 2, C goes to 3. G is the function 1 goes to X, 2 goes to Y, 3 goes to Z, and 4 goes to Z. And so then I look at the composition, G composes F, A goes to X, B goes to Y, and C goes to Z. This composition is injective. It's because all of the elements of A have unique images, but G is not injective since g of 3 is z, and g of 4 is also z.